Hello, and welcome to this lecture in GEL109, where we're going to be discussing Chapter 1, and this chapter is on understanding the Earth, that the Earth is a dynamic and evolving planet. So the first thing we're going to talk about is the scope of geology, basically that geology is a science and how this science is affected by many interacting spheres. In this case, we're going to talk about four of the major ones, and plus what's going on underneath the lithosphere. We're going to talk about the difference between hypotheses and theories. We're going to talk about the Big Bang, the solar system, and planet Earth. Talk about plate tectonics. Obviously, you can see how we're going from big to small. We'll talk about the rock cycle. We're going to talk about organic evolution, and we're going to talk about geological time. Now, be aware this is sort of laying out the entire semester, and that's what most books do, at least science books, in the first chapter. So geology is a complex integrated system of related parts, components, or subsystems. That's what I say in the notes. And it is defined by the interaction of the lithosphere. In this case, I have old marks here. That's funny. The lithosphere, which are the plates. It's basically what we're going to talk about when we talk about plate tectonics. But the core heats up the outer core, which supplies heat to the mantle, which causes the plates in the lithosphere to turn over. And when it does so, it affects the hydrosphere because it's going to change how the plates, the physical geography of those plates create rivers or lakes or where the oceans are, etc. Where if you're on the north or the south, you're going to end up with glaciers or not. And obviously, wherever these mountains are or things on these plates can affect where storms appear and how they affect the surrounding biosphere or et cetera, going back the other direction. And obviously they're all interconnected. That's what you see with all the different arrows. And I'm not going to read all the different text that's in the slide. It's from the book, so you can look through it. But basically, you should know that all of these different spheres are interconnected. You really can't separate one out from the other. But throughout this class, we're going to make connections between the atmosphere, biosphere, hydrosphere, lithosphere, and we're also going to say how those affect the mantle and the core, or vice versa, how the core and the mantle affect the four spheres. And we know that geology, meaning geo or earth, is the study of, ology being the study of, is the study of Earth, and it also is the study of other planets and their moons, which is where we're going to talk about, where all of these planets came from. And in this case, we're going to be discussing physical geography as well as some biology and some atmospheric sciences and hydrology. But primarily, this class is discussing the materials and the processes which compose and operate and change the surface of the Earth. Now, historical geology, which is also a component, we're going to be looking at the origin of evolution, from evolution of rocks and what Darwin was looking at. We're also going to talk about the Earth's continents, how they change, how the oceans change, the atmosphere, and how, theory of evolution and the biosphere and how that changes the planet, or what has gone on in the past. But the first thing we need to understand is what is science, or in this case, I'm going to talk about what is a theory. So one interesting situation is most people, including physicists, when they talk about I have a theory, that's not the theory we're talking about when we say a scientific theory. A scientific theory is derived from the scientific method, which involves, gathering and analyzing facts and formulating hypotheses, which are strong inferences based upon observation and measurement. So that's what I'm talking about right here. And we explain the phenomenon or processes that are outside of us. This is the real world kind of stuff that has nothing to do with humans. And I equate the process similar to you understanding that belief does not affect the way the world functions. So students ask me, do I believe in evolution? I say, no, I don't believe in evolution. There's no reason to say you believe in evolution, because saying you believe in evolution is like saying you believe in gravity. And I address this in some later lectures. But in this case, you have a process where you're testing a bunch of hypotheses, which are these strong inferences about the way the world works, and you're rejecting anything that doesn't work. And when you reject a hypothesis, you have an alternative explanation, which is another hypothesis that gets into place of it. So finally, proposing a theory, there's no one human that proposes a theory. That's also a misunderstanding. The theory is based upon observation measurements from the natural world, and it's a reliable explanation, solid explanation of the world, of processes in the world supported by a large amount of evidence. In some cases, or in most cases, millions of tested hypotheses. And in geology, we have many things. We have plate tectonics, which is an important theory. We're going to talk about, well, we're going to talk about a bunch of them. But so just be aware that when you talk about a theory, and I'm going to give you a blank slide in a second. I'm going to show you what this means. When you talk about a theory, it's a significant thing if you're talking about it in reference to a scientific idea. So this is what a theory is in science, and I'm gonna draw some pictures for you. So I'm gonna draw a circle, and this circle is basically just an idea, or not an idea. It's a representation of many ideas, and we're gonna put in this bubble theory, and then outside this bubble, which should be arrows, right, showing you or giving you an understanding about all of these things that we understand about the way the world works, contribute to this idea. And these are all hypotheses. I can, do H1, 2, 3, 4, ... I can go on to a million. So what happens, let's say I come along and there's some idea, some observation of the world. I can say theory of gravity. There's some idea about gravity here, that we think the world works in a certain way, and there is an alternative here of H naught sub 1. Well, let me reverse that. Actually, I should say H. I should say H1 sub naught. This is hypothesis. This is the null hypothesis of this hypothesis. And you test this hypothesis, you make an observation, and you're a scientist, you make an observation, you realize that your understanding of the way the world works isn't very good, and so you're going to say, well, you know what, this observation, I've now gathered data, and that's not the way gravity actually works for this one observation or this small idea in reference to some process that is a part of how we understand gravity. So you reject it, right? This is a rejection of that null hypothesis. And because this is a hypothesis and it can be rejected, you're going to say, okay, I have an alternative hypothesis, H1 sub 1, which is your alternative explanation of what's going on, and that's a better approximation of the way the world works. Now, when you posit this and you publish a paper on it and all of your peers review it, this then comes in place of the one that was there before. It's still H sub 1, but now it's a better explanation. It's H sub 1, but now this becomes the null hypothesis, which means it's the way we understand the way the world works right now. We can test many other hypotheses this way, and eventually we just keep rejecting them until we come up with a good approximation. Now, those hypotheses are only as good as the data supports them as being good. Now, here's the big kicker. This idea, this theory right here, didn't go anywhere. You don't reject theories. You only reject hypotheses. And when you reject these hypotheses, the theory, which is this right here, changes but never goes away. And this is quite interesting, and we'll see this in a little bit later. The theory of gravity isn't really well constructed or understood. We have the theory of evolution, which is another theory in science, obviously. We understand evolution much better than we understand gravity. But yet, I don't think any one of you would say that I deny gravity, or you even would say that you believe in gravity. It doesn't make a lot of sense. You don't have to believe in gravity when you get out of bed. You're not going to fly off the bed and hit the ceiling. it's going to work. Same thing with evolution. It's a process outside of us, has nothing to do with our belief systems, that works. And really, it's just a numbers game. But the fact is the theory of gravity, theory of evolution, all of these ideas are tested just like this millions and millions of times. And so there is when we talk about people will talk about creationism or in response to the theory of evolution, but in fact, there was James Ussher actually came up with creationism as a hypothesis of evolution. It wasn't organic evolution, but as a process of evolution in like 1550 or 1530. So when we talk about creationism, yeah, it was a hypothesis that was presented as an explanation of the way the world works, and it was summarily rejected. So when people talk about creationism as a alternative to the theory of evolution, they truly don't understand what's going on in science, and that's one of the big issues that we have, that people fundamentally get a hypothesis or hypotheses confused with theories. They are significantly different. And here's the other thing. A hypothesis doesn't become a theory. You can see right now a hypothesis is a piece of an understanding or this approximation of the way the world works, how humans understand it. It's one hypothesis. And there are millions of hypotheses explain the theoretical understanding. Same thing with the theory of evolution or any one of these things. So that's why when people will come up to me and ask me, because I do study evolution, and I study rocks, and I study geology and gravity and all these things. When you do physics or anything, you have to fundamentally understand that the hypotheses don't become theories, and obviously theories don't become laws. That's also a misunderstanding. Laws are just simply phenomenon, observations, and measurements that can be modeled mathematically. We actually have some of those models in evolution. We can model Hardy-Weinberg equilibrium, which is something that we know we can model it, and it happens the same way every time we model it using mathematics. And if it weren't for all of these confusions about science, we would have laws of evolution. We'd also have a much better understanding of what that means when we talk about it. We're going to go in depth later on in the class about this. So moving on. Okay, so what does geology give us, or how does it affect our daily lives? We know that obviously this is a baby, well, or a drawing of a baby, a baby showing you all of the things that a human will use in their lifetime, the amount of materials that they will use. So obviously we're affected by the geological resources that are available to us. We also have to understand geology so that we can look at, so we can avoid the major natural disasters or we can respond to them well. We also have economics and politics. It's also defined by our resources. Think of oil. We have our role as decision makers. How do we respond to changes in the environment or changes to our resources? Global climate change is another one we'll talk about. We have consumers and citizens. That's you and I, or possibly you are a politician. So those are the kind of things that we have to consider is how do all of our decisions in politics, economics, et cetera, affect the consumers and citizens and their quality of life. And then we have sustainable development, which is, well, there's really only one way to look at it is if we aren't doing something sustainable, that means it's going to end. So we have to figure out how to be sustainable. And in fact, most scientists would argue that what's going on today, the biggest problem facing us is there are too many people. And that's because we have a population that is unsustainable given the current situation or our standards of living, especially in America. And we are compounding that by as people become middle class, which is what we want them to do because actually their impact on the earth drops when you get better educated, et cetera, except for use of resources, obviously. But the increasingly larger population must be fed, housed, and clothed, and we must reduce the amount of impact they have on the environment. The greenhouse effect is another issue that I find fascinating when we look at politics. For some reason, there are no conservatives or liberals or most would say that, yeah, the greenhouse effect is a problem. The issue isn't so much that the greenhouse effect is happening. It is that we don't like the answers that we come up with when we address the issue. So it's basically the greenhouse effect is a known process. It's been studied, and actually we saw the effects. There's some scientists that were studying this, and it was actually, I think, predicted it to be a problem in like 1870 or 1890. I can't remember. I have some other notes related to that, but the greenhouse effect is known. It's been known for well over 150 years, and we see the shortwave radiation coming in, and it heats up the Earth and turns into long-wave radiation. It gets re-radiated. Some of that radiation gets absorbed by certain gases in the atmosphere and gets re-radiated in multiple directions, but more of it gets radiated. Basically, it bounces around, doesn't get radiated straight back down, but it bounces around, but the heat sink of the atmosphere stays warmer near the Earth, and so obviously less heat gets out into the upper atmosphere. So we increase the concentrations of greenhouse gases, which in turn increase the amount of trapped heat. And this is a result of humanity. It is. And we'll talk about that, and we'll look at graphs related to that, and we even have a section on the greenhouse effect. And it is a problem. We need to we need to figure out how to address it. So when we look at the universe started out as, well, a singularity. Think of it as a white hole. So a black hole, which is very dense, but it's at a spewing out. It's not a spewing out because it's not even the Big Bang in a sense. It's actually a great expansion. It's really, an expansion. Basically, if you are in the universe when it was let's say it was the size of a walnut, which doesn't make any sense because the universe is infinite by definition. It's the universe. So if you're in the small, densely packed, ordered universe, it's going to appear as infinite as if you were out here where we are today. Right? So as it expands, time is also moving in response to this. This is how we observe time, as the expansion of the universe, and that's set by, by the expansion rate. It's interesting because I was actually listening to a program, and they were interviewing an astronomer, and the astronomer said, remember, there are galaxies and stars that are an infinite or almost an infinite distance away from us. So their light will never reach us, and we will never be able to contact them. And that blew my mind because I was like, why isn't the sky filled with light? Like it should be, there's so many stars, etc. There's just so much matter out there. And the astronomer said that's interesting because the universe is infinite, there are things that are infinitely a distance away from us that we haven't seen. And what's also interesting is when you look with a telescope, say you're in here and you look back in time, which is really what you're doing, you're looking back to where some of these objects are 13 billion or 12.5 billion years old. You're actually looking back in time, and you're looking at objects that what they looked like 13.5 billion years ago, which is also just blows my mind because basically we are trapped in a very short time frame, even in our lives, where most of the things we look at that are of great distance away, say 14 light years, we don't know if that thing still exists because we're looking at light that is reaching Earth from 14 years ago. And that's still mind-blowing to me, and because it's the universe is a big place. But looking at different rates of expansion and what's going on, the scientists, the astronomers have decided or evaluated the universe and said it began approximately 14 billion years ago when they look at the expansion. And it started as an extremely dense hot body of matter that was almost completely ordered. Now, why it expanded and cooled, no one knows. We don't know what started it. But in this case, we do know that it started about 14 billion years ago. And this kind of gives you an idea of what happens as it expands. When it was a very hot, I don't want to say hot, densely packed area because it's still infinite, and that's what confuses people, I think. But it was a very ordered, hot, densely packed area. I don't even know how else to explain it. But we know that the universe expands from a central point because a lot of the objects experience the Doppler effect. It's sort of like, I think they use raisin bread in the book. They're all moving away from each other. That means even if it means that the universe is becoming fluffier, if you want to think about it. It's like the raisin bread that is rising, and things are moving away, and it's becoming less dense as more area in this infinite space, which again is mind-blowing. Can't really explain it, but because we're talking about 10 or 11 dimensions, and we usually only think in 4. But if you pull up the website and go to powers of 10, I'm going to just point on it here. I'm not going to click on it. You can look at how big the universe is. It actually goes down to the Planck constant too, which is also how small it is. It's a really interesting powers of 10 little Java website. It's pretty interesting. So the universe is expanding from a central point, and we know that the universe is filled with this pervasive background radiation. And most astronomers um, that evaluate this background radiation has a specific signature, and they think that's the faint afterglow of the Big Bang. And that the area which you see where the Big Bang started, or the expansion started, they can actually focus their telescopes back to certain regions of the universe and actually see these um, prototypical galaxies. So they're a little different than the galaxies we have now, but again, they're from 13 billion years ago. But they're again looking back in time. But as the expansion, as this is very hot, several 200 million years after the expansion, we start getting protons and neutrons, things cool enough where they start, um, things are not so excited, they're not in their elementary particles anymore, and they start forming the actual parts of the elements. And then about 350 million or approximately 400 million years after the Big Bang, you end up with hydrogen and different elements start sticking together, but it comes all the way out to where we are now. And we have all the different elements that have been absorbed by stars and spewed back out. Now remember, you are stardust. I know it sounds cheesy because of the song, but you are stardust. You are the result of 14 billion years of universal universe evolution. And all of the atoms and everything that are in your body and around you came from that expansion. And all of the particles and everything, or the energy contained within your system, has been around since the dawn of time. And it's also mind blowing. But remember, when Einstein was talking about E equals mc squared, where the amount of energy in a system is equal to the mass times the constants of the mass, whatever the mass is in kilograms or whatever, and times the speed of light, which is, um, it's a very large number. And if you look in the book, I think they do list the speed of light, which is 300, well, it's 209 but about approximately 300 million meters per second. So it's moving. And this basically creates a situation where eddies can form, right? Or areas where different matter can sort of stick to other matter and start forming elements, and the bigger elements are formed, et cetera, in stars, and you end up starting to form a solar system. So here's our solar system. We have a sun. We have 8, 9, 10, 11 planets, depending on who you talk to, but they threw out Pluto, and they were thinking of bringing Pluto back in. But originally there were 9 planets. Now they say there are 8 planets, and Pluto is a dwarf planet, of course. But we have numerous moons, asteroids, comets, and we think this all started happening about 4.5 or 4.6 billion years ago, and that's the result of when specific meteors hit Earth, and they haven't been subject to specific changes due to the atmosphere or whatever. We look at the radioactive isotopes in the meteors, and we can date these objects back to about 4.5 billion years, which is, they figure they're the original material that made up the planets, etc. But this is how our solar system started. It started out as this huge proto-solar system. So that's pre, and it's a huge rotating cloud of dust. And this rotating cloud of dust, certain things that are bigger or start sticking together, different elements are in there. So think of water vapor. Water vapor will cling to itself. It has a specific polarity to it, which makes it sticky. And then certain elements, rocks, carbon, other things will start getting absorbed, and you start forming these bigger and bigger particles. And they end up getting a spin to them. Like here we have a spin going this direction, and you start forming this proto disk, which again is an early disk, and you start getting the the lighter elements, the hydrogen stuff in the sun. There's heavier elements in the sun too. It's just at the center, but they start it, and there's so much gas, this hydrogen gas and material, that it's very dense and very large. It's like millions of times bigger than Earth. You get the idea. And it ignites. And also, when this is going on, you have other eddies that are forming. These are Lagrange points and other things that are out in space, and you start collecting, it's gravity points where there's more gravity in one specific area that exerted due to the sun's gravitational pull on the other particles, and you start getting protoplanets forming. And these materials form and it's basically a big rotating cloud. So nebulas, the nebulas you see, are actually could be forming planetary disks or solar system disks. And we think this happened again, like I said, 4.5, 4.6 billion years ago. As it condensed and collapsed due to gravity, you end up getting the planets forming. And we think that Earth sort of looked like this. You have the sort of really hot radioactive Earth, not very dense. We're still getting more and more material on Earth every year. I think several million tons of stuff falls from outer space. And anyway, the Earth was uniform in composition and density because of the heat and the radioactivity. As temperature cools and the early Earth reached the melting point of iron and nickel, which then starts migrating to the center. And it does this because, as it says in the book, these are denser than the silicate minerals, which tend to be the rocks that we have on the surface. There's still nickel and iron on the surface, obviously, but it's because it's not a completely uniform set of layers. But we have the crust form, and the mantle forms, and the liquid outer layer, which gives us the magnetic field that keeps us alive, and then the solid inner core, which is that nickel iron material. And we end up with, just a second, a layered Earth, which is, we have the crust, the continental crust, oceanic crust, which is what we're going to talk about in this class, along with the other spheres. You have the upper mantle of the asthenosphere, which is like GAC. I don't know if you guys ever played with GAC when you were kids. It's basically cornstarch and water, and when you grab it in your hand and hold onto it with some force, put pressure on it, it solidifies because the starch granules stick to each other. And when you release it, as your hand heats it up, it turns into a sort of taffy-like liquid. Well, it's even a little. It's not as solid as taffy, but and that's so there is a sort of semi-melted portion of between the upper and lower mantle. And we have three concentric layers formed, which are the core. Now the outer core and the inner core are basically considered the same thing. And then you have the mantle, and then of course the crust itself at the very top, the lithosphere, which is the crust in the upper mantle, the solid outer part of the Earth. Due to differential heating from the inner and outer core and different radioactive isotopes moving around down there, we end up with upwelling of heat. And this upwelling creates convection cells or convection currents, just like we have on the surface of the planet when you look at the atmosphere and where our big storms come from. These are big convection cells as well. But it's a turning over of the rock. So you get an upwelling, which causes magma to come out the top here. We get an oceanic ridge, which then pushes this oceanic plate. And the oceanic plate, because it hits a less dense continental lithosphere, starts diving down into the mantle. And as it dives down in the mantle, it pulls the stuff behind it in this direction. And as it does that, it melts, and there's another convection current over here, and it goes down further into the mantle, reaches the outer part of the outer core, and heats up again and then gets turned over. This can take obviously tens of thousands to millions of years. It's very slow. But nonetheless, these things get turned over, and you get plates, many different plates. We have 6 plates under, I think, California and Arizona, where they just got stacked up as they got pushed down. And it's pretty interesting. I think if you guys do, when you start looking at the different literature out there, one of you may find that article. But the lithosphere is composed of these rigid plates that produce different kinds of interactions. So one is the divergence up here. So this is a divergent boundary. This is a convergent, which produces the subduction. That's a convergent boundary right there. And then as these slide apart, you see these little lines right here. These will slide across each other because one of these plates will be moving faster. It's a section of the plate next to it, and that will be where they slide past each other, and they're called transform boundaries. And all of these plates are divided up, and you can look at them. They're being destroyed and created all the time, but right now this is what it looks like currently. I'm not going to ask you to memorize these, but be aware of the major interactions. For example, we have the Juan de Fuca plate, which creates a lot of these earthquakes and tsunamis, which we haven't had in like 50,000 years or something like that, or I don't know how long ago, but along the Washington and Oregon coasts. And we had the tsunamis from the Japan Trench right here that caused problems for Fukushima, which caused that meltdown. I don't know if you guys remember that. I'm sure you remember it, but maybe it's not on the forefront of your mind. But if you look down here, they'll show you all the different ridge actions, the transform faults, ridge axis, subduction zones, and all the different zones. And you can say, oh, look, right here we have a transform fault, which is the San Andreas, which goes down into the Bay of Baja. And then you have a subduction zone right here, which is a convergent boundary. Then you have a bunch of transform ridge axes from the Juan de Fuca plate. And eventually the North American plate, as it gets pushed from the Atlantic, mid-Atlantic ridge, will push the North American plate over Juan de Fuca, and pretty soon the Juan de Fuca will be gone, and you'll just be sliding over the top of the Pacific plate. Which leads us to plate tectonic theory, which unifies our understanding of the geological features and events like earthquakes that we experience on Earth. So, one of the processes when you look at plate tectonic theories, you can make a model, which is what this is, and you can predict what's underneath each one of these structures. And we know that like the Aleutian Islands, they look like this. There's a oceanic plate that's diving underneath another oceanic plate, which causes melting. This is like a boot effect where you're losing, it's all based upon temperature and pressure if you're going to remain solid or not. And as the pressure is released but the temperature doesn't change, the top of this oceanic plate melts, and then of course it's less dense at that point. It starts moving up through the upper mantle, and then of course up to the surface and producing volcanoes, etc. And then we have a land surface here where you have an old oceanic plate that eventually, because so many volcanoes and everything, filled in this back basin here, which would be this area as well over time. Well, no, actually we have a divergent boundary there, but it fills it in, and eventually this plate here, this oceanic plate, may actually get frozen in this part, or eventually it'll move down and get melted completely if this continues moving in this direction. But it looks like this will stall out at some point because you don't have anything. Well, no, eventually this will get pushed over and this will be destroyed. But anyway, so you produce all of these different structures which are predicted based upon plate tectonic theory. So you have the transform plate boundaries. We now understand them based upon plate tectonic theory. The mid-oceanic ridge, the divergent plate boundary, just like I said, where there's one over here. And why mountains? We have these continental oceanic convergent plate boundaries, which make these island arcs on the continents. We also have the oceanic convergent plate boundaries, where you get the island arcs on the Aleutian Islands. So in the ocean, and then so this would be, I don't know, think of the coast of Oregon and Washington with Mount St. Helens, etc. And then this would be the Himalayas, because you have two continents running into each other. In this case, it's like a train wreck, and they just stack up continental material because it's less dense than the oceanic, but they're of the same density on either side, so it's like a train wreck. This process also explains the rock cycle, which means based upon what we know how magma moves, how it crystallizes, and the movement of the plates, plus heating from other magma chambers once you get sedimentary rock, tells us where all of these different rocks come from. So you get the melting, you get an upwelling of the magma as it moves through the country rock here, it crystallizes, and you get these huge deposits of igneous rock. In this case, they're saying it's intrusive, so this would be intrusive rock right around this neck of this volcano. And then you have consolidation of the different igneous rocks. You also get extrusive lava, and consolidation means it gets all stuck together and more rock gets put on top of it, or more lava, etc. And eventually you get specific kinds of rock. That will weather due to exposure to the atmosphere, rain, whatever. Could be plants. Be biological weathering, or just freezing of water. We've seen that in the roads of Michigan. They're not actually that great, but that's all due to the weathering process. And then it gets transported due to water. You get deposition, again, lithification, just like you get consolidation over here, which is compaction and cementation from specific kinds of chemistry. Could be calcium carbonate, etc. Could be silicon dioxide if it's in the water, if it's hot enough, and you get these sedimentary rocks that are formed. And then if they get heated, the sedimentary rocks will become plastic in the sense they get really hot, but they don't actually melt. And then specific minerals migrate in the rock and they line up and you can get banding. Sometimes some are banded, some are not. But anyway, this is the whole rock cycle, and you can look at follow just like we follow the different spheres, you follow the different arrows and it'll tell you what's being formed. So you can have, here we have igneous rocks. If you go over here and expose those igneous rocks to heat and pressure, you end up with metamorphic, I don't know, granite, and it's called metagranite because it's not actually granite, it's metamorphic granite, and it looks a little different than the granite itself. But we have three types of rocks. So three types of rocks would be igneous, sedimentary, and metamorphic. And these rocks are produced by three different kinds of boundaries. So you got the divergent boundary, which spews out a lot of magma. You got the convergent boundary, which causes the plates some subduction, which causes melting of one plate, which then causes volcanoes, and then you get different kind of rocks formed that way. And then you got the transform faults that we didn't really talk about, which will put certain rocks under pressure and heat depending on where they are, and will go through metamorphism. But in fact, you end up then weathering all those rocks. So you got the igneous, sedimentary, and metamorphic rocks coming from the primary source of the rocks is the divergent, convergent, and transform boundaries. I'm going to go quickly through these. So this is an intrusive and extrusive igneous rock. We have basalt and granite. You know that this is intrusive because you can see the crystals. This is extrusive because the crystals are very small, or they're smaller than 1 millimeter. Usually we define an intrusive or extrusive rock based upon that 1 millimeter mark. Here we have a conglomerate, which is basically, think of a river pebbles that get covered by a whole bunch of rock. Eventually they get pressed together and they start interlocking, either due to just pressure or some chemistry that's in the water that may be covering them up. And you got limestone, which is precipitation from seawater of obviously the calcium carbonate from the animals that are in the reefs or something that's close to shore in most cases. But these are rock mineral fragment types of rocks. They're sedimentary rocks, and it's precipitation of minerals from solution that stick these together. These individual pieces are called clasts, and then they're the stuff that's stuck together. And it's usually the compaction of plant or animal remains or other materials that are already there. Then you got the metamorphic stuff. This is gneiss, and this is quartzite. So this is a banded metamorphic rock. This is a non-banded metamorphic rock, and this is due to heat and pressure and sometimes chemically active fluids, which then change the chemistry, which is really what you're doing. You're changing the chemistry of the rock due to heat and pressure, but you're not actually melting them. Remember, this is all chemistry. Everything that we talk about is a chemical reaction. Even when we talk about rocks, we often don't think that way, but that's what it is. Geology is basically chemistry and how things that are naturally in the soil or in the ground stick together or change. So how are the rock cycle and plate tectonics related? This will be a question that I ask you on an exam, so it's something you want to make sure that you can connect. The rock cycle, so we have the different melting points when you're going to get different kinds of igneous rock. This is slow cooling igneous rock, so you're going to get the granite material down here. Fast cooling rock, when you get near the surface, is going to be like the basalt. You're also going to get the metamorphic rocks formed next to these big igneous chambers. You also get the sedimentary rocks formed once you get the continent, all this material falls off and starts layering up, etc. And then you got, anyway, you basically connect the rock cycle, which, if you remember, there are three different kinds of rocks to each one of these features that you see here. So you can just say, okay, we'll put igneous rock here. I'm just say I draw a line up, say sedimentary rock here, metamorphic rock, line like that. You say, well, you got erosion, you get the idea. You say igneous rock forms right there, sedimentary rock is right there, metamorphic rock will be near heat and pressure. You get the idea, so you can figure out how to connect this rock cycle, how things change, to plate tectonics. Or as I say in the notes, I say plate movement is the driving mechanism of the rock cycle. Plate interaction determines to some extent, not all of it, which of the three rock groups will form. Then we talk about organic evolution and the history of life in this class. So we know that basically we know that the plate tectonics and organic evolution changed the way we view the world. And it actually is very powerful because we cured a bunch of diseases, and we understand why vaccines work, and we understand why we can make the lives of humans better based upon these different ideas. Um, anyway, the theory of organic evolution, which is derived, I mean, Darwin figured it out from what Hutton was doing, which is another a geologist, and connected the ideas from the evolution of rocks to the evolution of animals, along with some artificial selection, which we'll talk about at the end of the semester. But basically, that all living things are related, and they all descend with modification from a common ancestor, or organisms that have lived in the past. And Charles Darwin, proposed the mechanism of this change as natural selection, which basically results in the differential reproduction and survival of specific variants of organisms in a population, which is a lot of gobbledygook, I realize that, but basically it's survival and reproduction of organisms that are best suited for the environment. And we're going to talk about that at length at some point. I have a lot of information related to uniformitarianism and Charles Darwin and natural selection in the notes of this slide, if you want to take a look at it. But basically, we know about the fossils, and we connect the linkages of these fossils, and as they change through time, we can actually give us a geological record based upon organic evolution and uniformitarianism, which basically states that, and this is actually the fundamental tenet of geology, the cornerstone of geology, that laws of nature have remained unchanged through time, and thus all the processes that we observe today also operated in the past. And there is a possibility they could operate at different rates, and that's rates of evolution, etc. But it's not like time changes. It's just the rates of evolution just means how quickly the natural selection affects certain populations. But from that, we derived the geological time, and it's based upon living organisms. If you notice, the Cambrian, which is the first evidence of life or multicellular life, 542 million years ago, and it's from specific rock formation. But anything after that, there's still fossils and stuff, but it's not as clear cut, and that's because microbes don't fossilize all that well, and they don't look all that different unless you have living ones. And so there are different types of rocks and stuff older than 542 million years, but we do most of our explanation and changes of the Earth based upon the what we call the Phanerozoic era, or eon, sorry. But I want you guys to appreciate how much time we're talking about. It is a lot of time. I can't even conceive of a million years. We're talking about 542 million years. And so when we talk about evolution or organic evolution, we'll do some experiments, and you'll see, or at least labs, you'll see why this is really significant as to when we're dealing with the numbers of organisms and the amount of time that operated upon these organisms to allow for change. Okay, so geology is complex, just like we talked about. It's an integrated system of related parts, components, and subsystems. We know that hypotheses are testable. It's a testable inference, which means it's based upon observation and measurement. And a theory is a well-substantiated explanation of some aspect of the natural world. That means it's out there, doesn't have anything to do with us. It's going to go on if we're here or not. And our understanding is based on this body of facts that have been repeatedly established through observation and experiment. Those are the testable hypotheses, or the testing that has gone on. And then we have this reductionism in geology, where we start at the universe to understand the solar system, to understand the Earth, to understand how plate tectonics work, to understand how rock cycle works, to understand the rocks, to understand the minerals. We're actually going to go even further. We're going to go down to talking about the individual components of elements, and then how the interacting spheres give us all of this change in the rock cycle, and how the rock cycle gave us rock evolution, which then gave us an understanding of the organic evolution, and how that's a process like gravity, meaning that it's out there, has nothing to do with us. It's just a process that goes on, and it's an information idea, actually, just like in the rocks. It's basically your current form is based upon past information. And then we're going to talk about geological time. Sorry, we talked about geological time and uniformitarianism, but that's also going to be a topic later on in the semester. Thank you, and I will post another video probably coming up next week on chapter